Okay, Newton's laws. Hopefully you've already done some of the investigations and read the textbook about Newton's laws, but we'll go through them in detail here. So Newton's first law is what I call the law of inertia. And inertia is a property of matter, just like mass or color or shape. And this property is the resistance to change. So all objects want to resist change. They want to either remain stationary, as this block here is stationary, or they want to remain in motion. So if the block was in motion, it would want to stay in motion. The only thing that can affect a change to that motion is some external force. So the reason a block wouldn't keep sliding along our tabletop is because of the friction between the block and the table. That external force brings it to a stop. If I push that block into outer space where there is no friction, it would just keep going and going. And Newton's second law is basically the equation F equals ma. So it describes the relationship between force, mass, and acceleration. And Newton's laws, the force is measured in units called newtons, obviously for Sir Isaac Newton, and that is capitalized with an uppercase M. So the force on any object is equal to the mass times the acceleration. So 1 Newton is going to be equal to a kilogram for mass times acceleration, so a meter per second squared. So 1 Newton is 1 kilogram meter per second squared. So in other words, 1 Newton of force is the amount of force required to accelerate a 1 kilogram mass at 1 meter per second squared. So if I had a force acting on this object in this direction to the right of 1 Newton, and it was a 1 kilogram mass, this 1 kilogram mass would accelerate to the right at 1 meter per second squared. Okay? So that force causes an acceleration. And then Newton's third law is that for every action there has to be an equal and opposite reaction. So right now this block is exerting a force downwards due to the force of gravity, right? Fg. And the force of gravity is going to be equal to the mass of the block times the acceleration due to gravity. G is 9.80 meters per second squared. So this block right now is exerting a force downwards into this surface. So because it's exerting a force or applying an action to this surface, the surface must be exerting an equal but opposite force upwards. That force upwards we call the normal force, Fn. Okay, so Fn is called the normal force. And it's the force that a surface exerts on a mass, and it's always going to be perpendicular to the surface. So if the surface is horizontal like this surface, the normal force will be perpendicular to it. Later on we'll see if the surface is at an incline, the normal force will also be perpendicular to that surface, so it will be at some angle. So in this case, the normal force is going to be equal but opposite to the force of gravity. And that's Newton's 3 laws basically in a nutshell. So whenever we're going to be using Newton's second law, F equals ma, we're going to be drawing what's called a free body diagram. And a free body diagram is basically a vector diagram. And it's a special type of vector diagram. Normally when we draw vector diagrams, we always add the vectors head to tail like this, right? Free body diagrams are slightly different. What we're going to do is look at our object, in this case this block, and we're going to draw all of the forces starting from the center of mass of this block. So if you can imagine the block having a center of mass right here in the center, so the force of gravity obviously would be straight downwards. And just like we had before, there will be a normal force acting upwards, equal but opposite to this. Right? So you can see our vector diagram looks slightly different. The tail of every vector is starting at at the center of mass. If there was another force, say I was pulling this object to the right, I would draw that force starting at the center of mass. And there might also be a force of friction resisting this motion. So this is a basic free body diagram. Okay, it's a vector diagram of the forces. And we're going to use our free body diagrams to determine the net force on an object. And we know the net force is going to be equal to the mass times the acceleration of this object. So what we're always interested in is what is the net force in the direction of the acceleration. So you'll need to look at your free body diagram and decide which way is this object going to accelerate. Right now, I know that it's probably going to have an acceleration in this direction. This is the force that's applied to the right. There's a smaller friction force opposite to that. These two forces are equal and opposite, so there's going to be no acceleration vertically. So the only acceleration will be to the right. So when I look at my net force, the net force, again, is always going to be the sum, and this Greek letter sigma, that looks like a funny shaped E, is the sum of all of the forces. And again, we're interested in the sum of all of the forces in the direction of the acceleration. So in this case, I have this force F in the direction of the acceleration and friction opposite to the direction. So I put it in as a negative because it's in the negative direction. Those two forces together cause my mass to accelerate. So now I can write in my force that's applied, calculate the amount of friction using the mass. I would then be able to determine the acceleration of this block. So hopefully now you understand Newton's three laws a little bit better, and you understand how to apply Newton's second law, which describes the net force, and how to draw a free body diagram. So try some of the questions, the sample questions in the textbook, and in the next video we'll do some more work with friction and free body diagrams.